Welcome to the first supplementary video for one-dimensional motion in the kinematics unit of AP Physics 1. In this video, it's going to be a little different as I'm speaking off the cuff rather than being scripted, but just to cover not so much things that were missed, but something that is important more for problem solving and to show skills that will be useful later, specifically deriving equations. So, what I wanted to do with this one was, if you've looked at the equation sheet for AP Physics 1, in kinematics there are 3 kinematic equations, or at least main kinematic equations, and in the video I only really covered 2. So this third equation, which is not an eraser, this equation, v squared equals v naught squared plus 2a delta x. That equation is useful for solving problems, but unlike the other 2, its origin is a bit more unique. So what I wanted to do in this video was to go over or talk about the origins of this particular equation as opposed to the other 2, and in the process we'll also be showing some useful skills for deriving equations that are going to be used throughout the entire course. All right, so the ones we went over in the video were the definition of acceleration, v equals v naught plus at, and then the other one is the displacement curve, which I prefer to write like this, plus 1/2 at squared. Sometimes this one is written in a slightly different format where you have x equals x naught plus b naught t plus 1/2 at squared. These are the same equation. I've just taken the x naught term and subtracted to the other side, and you get the change in position, which is just displacement. It's a little easier to look at. And when we go over how these two relate to graphical representations, this format looks a little better sometimes. Okay, what this equation is a combination of these two smushed together. So here's how we're going to derive that. And at least for the purposes of the course, when we're talking about derived equations, it's mostly just manipulating variables, substituting one equation into another, or setting a bunch of things equal to get to the result that you want. That is generally a quick overview of how that works. So what we're going to do is I'm going to start with these 2 equations. I'm going to take this one and solve for t. So we're going to have p minus v naught equals at, and then we're going to divide by a. So you have v minus v naught over t, over a equals t. All right. Now, the goal of this is we're going to take this term, which is our time term, and substitute it into the times in the displacement curve, and then solve or simplify. So that's the goal. Because if you look at the equation we're trying to derive, there's no time in it. But there is a final velocity which isn't in the displacement curve. So we solved it for time, we're going to sub it in, and then just do a bunch of algebra. Or at least I will. So, see, delta x equals v naught. Then we can sub in our t term, and that'll be 1/2 a, and then our t term again, and that'll be squared. All right, and then we just solve it out. So we would have. So what we've done is, at least in terms of deriving, is we've taken this definition of acceleration, solved it for time, and then substituted it into the t's in the displacement curve, and then we're going to solve. At least in this case for v squared, and that'll get that. Assuming I don't mess up, it should give us the right thing. So that would be v minus v naught squared, because we distribute in, over a plus 1/2 a. This is going to have to be FOILed, so this top of the equation would be v minus v naught squared, which is v minus v naught times v minus v naught, And that should give us, ultimately, when you FOIL that, it should be v squared minus 2v naught v minus b naught squared. And that will all be over a squared. And we square everything inside the parentheses. Okay. So things we can cancel out. This a is going to cancel out that squared. And if you look, even though this side is multiplied by 2, we do have an a in the denominator for both, so they are going to be like terms. The only thing I'm going to do is I'm going to multiply everything by 2. So we're going to take this whole thing and multiply by 2. So that will give us 2 delta x equals, again, 2v naught v minus p naught squared. I'm sorry, that would be 2v naught squared. 2v naught squared over a. The 2 would cancel out this for that whole term. So you get v squared minus 2v naught v minus p naught squared over a. You have their like terms, so you can actually combine them. But I'm going to change color. Here is a positive 2v naught v. Here is a negative 2v naught v, so those will go away. Here is a, I'm sorry, there's a mistake. This should be, when you FOIL it, should be come out to plus v naught squared. All right, so this 2v naught v, that 2 would cancel out that because you have 2 and 1. Okay, so simplifying that, we get 2 delta x equals negative v naught squared plus b squared over a. Okay, it definitely looks like what we're supposed to be getting now. So we're going to multiply both sides by a, get 2a delta x equals, just rewriting this a little bit, b squared minus v naught squared. And do your final move over, you get v naught squared plus 2a delta x equals v squared. And there's our third kinematic equation that's useful for certain circumstances where time is not something you have, and you have two velocities and acceleration or displacement, whatever else. So you can see from this just a little bit of derivation. This is a particularly weird one just because you're squaring time and it's in multiple places, but at least gives a sense of skills that you should be developing, meaning up here where you need to solve for a particular term and substitute that into something else, and then just a lot of algebra solving and whatever else. And that should give you your result. I hope this helps a bit with some things, where that equation comes from, where it's useful, and some deriving tips, a good example of how to derive something. Stay tuned for the next video where we're to just do some practice problems in 1D kinematics, and then the next content video should be two-dimensional kinematics. Don't forget to like and subscribe.